Hello, I'm Yvonne Pignolet from Dfinity. This presentation is about the Ingress message lifecycle. In this talk, you'll learn how an update call is processed by the Internet computer, from when it reaches a node until it's been executed. In particular, we'll discuss the conditions that must be satisfied and how we ensure that the right parties can be charged for its processing. Remember, the Internet computer hosts canisters which contain code and data. End users can interact with them by sending query and update calls to the nodes which run the Internet computer protocol. Query calls can be answered by any node participating in the subnet hosting the destination canister. They don't change the canister state. Update calls, on the other hand, can change the state. Therefore, the nodes must agree on their validity and their order. They do this with our consensus algorithm. When a valid update call request is received at an Internet computer node, the HTTP handler of this node will create an ingress message out of it and submit it to the replica for processing. Before reaching its destination canister, an ingress message is processed by several software components. In a first step, P2P ensures it's broadcast to a sufficiently large set of other nodes. At some point, consensus forms a block that contains the message, and once notarized and finalized, it is passed to message routing, where it will enter the induction pool if it satisfies the valid set rule. In the induction pool, the ingress message may spend some time waiting in its destination canister's queue before the scheduler selects the message to be executed. Contrary to an inter-canister message, which is sent from one canister to another, the sender of an ingress message is a user, while the destination is a canister in both cases. Processing a message takes time, so a user cannot be directly told whether or not a message was inducted and executed, and what the result of its execution is. Instead, a user can get this information from the ingress message history, and extended results may require a query call in addition. To prevent the user from waiting until message gets executed for an unlimited amount of time, ingress messages can expire. And, last but not least, ingress messages are signed to guarantee their authenticity. All this information is part of an update call request. The HTTP handler transforms this request into an ingress message and then passes it on to the ingress manager. An ingress message has the following fields: the sender field, which determines the user, a receiver field, which is a canister, both represented by their IDs. Then the expiry field, which contains the latest IC time a message can be inserted in the induction pool. In other words, once the Internet computer time has exceeded this instant, the user knows that the Internet computer will never process this message. Since IC operation and storage costs are to be charged to an entity, the expiry time can be at most a constant in the future, because otherwise there could be unlimited costs. And the authenticity of a message must be guaranteed by a signature, verifiable under a public key. More details on authentication are explained in the corresponding talk by Björn. The method name field of an ingress message describes the canister method to be invoked for the update call, and its payload lists the arguments for the call. To identify otherwise identical calls, a canister ingress message can contain a nonce. The request ID consists of the hash of all the fields of an ingress message, with the exception of the signature. Based on this ID, a user can ask the Internet computer what the status of the request is. The details of all these fields are described in the interface spec. The Internet computer initially uses a canister pays model, in which the canister is charged for all resources that the Internet computer needs to run the canister. This includes storage, computation, network resources, but also everything that is spent on running the Internet computer protocol is factored in. As the canister pays for resources spent on processing incoming messages which are not directly under the canister's influence, the Internet Computer provides the canister with a mechanism to limiting the expenses. What I describe next is a very basic version of a more flexible and more comprehensive mechanism that will be available to canister developers soon. In the basic version, a canister can expose a method to inspect an ingress message and its fields and make a decision if this ingress message should be processed further or rejected right away. For this decision, the canister state and metadata can be taken into account. As an example, a canister could use the inspection method to only accept messages if the canister's current cycle balance is higher than a certain threshold. Or it can check that the sender of the message is part of an authorized list. Note that the execution of this method to determine if a message should be kept around is basically a query call. In other words, the canister state will not be changed by it. To be sure that a message can be executed and someone can be charged successfully for it, all the following conditions must be met at some point before execution. Note that this is really before we execute them and not before we send the message around in the subnet. So first of all, formatting must be correct. All the necessary fields must be present, they must be of the correct types, the request ID must be correct, and the message size must be bounded by the maximal size allowed, which is stored in the registry. Then we need to make sure that the message has not been expired when it is being inducted. And we need to make sure that it spends less than a given constant amount of time in the induction pool. We don't want ingress messages to be executed twice by accident. So if we have an ingress message with the same request ID as one that has been inducted before, then the second one will not make it into the induction pool. Other checks include WASM checks. So for example, the canister has actually an update call with the method that is sent here, and the arguments are correctly formatted. This may include some more strict size checks for specific methods. And finally, the method canister inspect message is either not exposed or it must return accept when called for this message. For a message to be executed, its destination canister must have a sufficient cycle balance, and there must be sufficient induction and execution capacity. Last but not least, the signature on the request ID must be verified. Now that we are aware of all the conditions that must be met for a message to be executed, let's follow an ingress message through its path until it's being executed and look at the necessary and sufficient checks at its different stations. The first component the update call request is submitted to is the HTTP handler, which is also the first place we can run some checks. If it passes them, the message is added to the artifact pool and disseminated via the P2P protocol. When receiving an ingress message from another node, so when it's not coming directly from a user, then the ingress manager carries out a set of checks before adding the message to the artifact pool, because it could be that the node that sent the message is malicious. And when it's been added to the artifact pool, it's being forwarded to other nodes. When the block maker creates a new block proposal, the ingress manager selects a set of ingress messages suitable for the new proposal and then broadcasts it. When receiving a proposal, the node runs another set of checks before notarizing the message. When the block has been finalized and its messages are passed to the message routing component, they need to pass the valid set rule before being inserted in the induction pool. And, last but not least, a final set of checks is carried out before a message is being executed. Before we dive into the details of each check, it's important to note that some of the conditions for the messages are impossible to get right very early in the process. When having to decide for an ingress message whether it should be added to the artifact pool, a node can only make use of currently available information. In particular, a node cannot know at this point in which block a message will end up and how the destination canister state will have evolved by then. It could, for example, happen that the message in the block right before the block that will contain the message is changing the canister state and thus causes the message to be rejected in the end. However, at the instant the decision has to be taken, there's no way for the node to know what will happen by then. Regardless of how complicated a mechanism we invent, there will always be cases where a node takes a wrong decision and either rejects a message that would later be accepted or adds a message to its pool, even though it will not be able to add it to a block later. As a consequence, we decided to invest as little effort as possible into validation before gossiping. And we will only drop messages that would never make it into a block. If in doubt, we opt for a version that is as user-friendly as possible. Note that we ensure with the selection and notarization checks that no bad messages end up in a block. Some checks are independent of the node's current state, so we'll always run those early, for example, formatting and signature verification. Some other checks do depend on the node state, yet they are monotonic in the sense that if a message is invalid at some point in time, it will remain invalid in the future. For those checks, it is fine to take the locally available state. For the remaining checks, it is possible to be wrong in both directions. According to the principles set out in the previous slide, we decided to take the locally available state when receiving a message from a user and simply accepting that some decisions will be wrong. If a message is received from a peer, we do not repeat these checks with the locally available state. In other words, we trust their decision and we accept the fact that we might waste some resources because of that. We will now go into more detail for the set of checks we're currently performing. Most likely, we'll add quite a few more checks to strengthen the platform soon. So the very first check is at the HTTP handler. When a user request is received, some first checks on the format of the request are performed. These checks do not need to be repeated by other components, as the deserialization mechanism will ensure that only correctly formed messages can be passed into ingress messages. In addition, the HTTP handler performs the following checks with respect to its currently available latest execution height, time, and latest available registry version. So we check if the destination canister is actually installed on the subnet. We check if the method and payload are correct, if the signature verifies, and if the expiry time is in the future, but not too much. Finally, we also make sure that the message under scrutiny is not in the ingress history or in the artifact pool. If the inspection method returns decline, then we drop the message. Otherwise, the message has passed all the checks and it is added to the artifact pool to be disseminated in the subnet. If a message is received from another node, then the ingress manager component checks if this message is suitable to be broadcast further. An ingress message is only sent to other nodes if all the following conditions are satisfied. We check the signature again to avoid wasting time when block making and for misbehavior detection. We check the expiry time and we make sure that the message is not already in the artifact pool or in inductive payloads. The ingress manager selects a valid set of ingress messages to be part of block payloads when prompted by the blockmaker component of consensus. This component also validates the ingress payload of block proposals received from peers when triggered by the notary component of consensus. In that case, the ingress payload of the proposal and the blocks of the chain the proposal extends need to be considered. The validity conditions for block making and notarizing are the same, and both of them refer to an executed height and the registry version stored in the block they concern. This information is available on all nodes and thus can be used to determine unanimously the validity of an ingress message. For example, all nodes can confirm that the expiry is within the correct bounds with respect to the time in the block, regardless of what their local wall clock time is. when a batch is passed from the finalization component of consensus to message routing, the ingress messages in the batch payload are subject to the valid set rule for capacity and cycles check before they enter the induction pool. Other checks do not need to be repeated. They are assumed to hold due to the threshold of nodes necessary for finalization. Messages which have been inducted but not processed for too long are discarded. A last cycle check is performed on ingress messages before they reach their destination, when they are selected by the message scheduler in message routing. Now that we've seen the overview of all the checks, we go through them once more. The HTTP handler is the first component that works on an ingress message. And here we basically do all the checks that we can. Format, time, we consider the registry, and of course we look at the user and its signature, we look at the inspection method, and we make sure that the message does not show up in the ingress history. Note that different nodes may come to different conclusions since they have a different state locally, but that's absolutely fine. And if all the checks are good, then we add the message to the artifact pool. And once they are in the artifact pool, P2P will make sure that they reach enough other nodes. When a node receives a message from a peer, then at the ingress manager, we don't need to repeat all the checks, but only some of them. We check the expiry again, we make sure it's not in the artifact pool already, and we look at the ingress history. And of course, we also want to verify the signature, because that takes time, it's a rather expensive operation. If all the checks pass, same thing again, we add it to the artifact pool, and P2P then broadcast it in the subnet. To make sure that we won't have too many messages in the artifact pool, we will remove expired messages from it. Also, for these checks, different nodes might not come to the same conclusion, but also here, that's fine. They might decide differently depending on which messages they have in their artifact pool already, at what execution height they are, and so on. Now it gets interesting. When consensus decides that it's its turn to create a block, then the block maker calls the ingress manager and tells it, please give me my next payload. And it tells it what is the executed height and what are past payloads on the chain that is being extended. And here it's not just since the last finalization, but actually the payloads since the last executed height. Then consensus also provides a time and a registry version, because all this information is necessary to pick good messages. What is particularly important here is that we make sure that the canister for which the messages are selected, that the balance, the cycles balance on these canisters is high enough. And again, if it has found a bunch of messages that satisfy this, then it gives this back to consensus. Consensus then takes this information and sends out a block proposal. When a node receives a block proposal from a peer, then its notary function comes into play. And as part of notarizing the block, where it does some consensus things, it also needs to look at the ingress messages. In particular, it needs to run detailed checks for all the messages that are part of the block proposal. And it needs the same information that was used for selection on the previous slide. And what is particularly important is that on the previous slide here, so when the block maker creates a payload, it doesn't need to check all the signatures again, because it knows that all messages that are in its artifact pool actually have a valid signature. But when it receives a block proposal from another node for ingress messages that he has never seen before, then it needs to verify their signatures. So this is a slightly more expensive operation. So you have seen that there are many, many checks that an ingress message needs to go through. And this is necessary to be able to charge cycles to canisters for the consumed computation, communication, etc., and to prevent users and malicious nodes from causing excessive resource waste. Thanks a lot for your attention.